All right, folks. Today we're going to talk about cellular automata. I talk a little bit about this sort of stuff in my CS1 classes as well, but we don't really sort of program any of it up. So that's something that we're going to do. We're going to use JavaFX, and we're going to do a 1D version for this lecture. And then I have a 2D version, which is the true sort of game of life, Conway's game of life, that we'll do in the next lecture. So I just want to give you an idea of sort of what we're going to use JavaFX wise to do this, and sort of the little bit of the math, which is not very complicated, behind this. And we'll actually create a relatively cool fractal out of this as well. So similar to our sort of Mandelbrot set, but not sort of the same type of math. So sort of behind the scenes here, I have a very basic JavaFX program, and it just displays a window right now, or at least that's all that it should do. And instead of using a pane, I'm using a grid pane. So we're going to talk a bit about the grid pane today as well as we use it. This is a very good sort of application for the grid pane. So I'm going to talk just about how you can use it. It's very nice for things that lie on a grid. So that's how we're going to use it today. And we're going to create a class and stuff like that to help us with this sort of cellular automata stuff. But overall, most of the code is going to be here in Start. We'll just have a little class that sort of helps us out. So make sure you have something like this ready after I go through the slides and give a little description of what this is. Then we'll jump in and do some programming. So back here, cellular automata is essentially a good example of things like 1D and 2D arrays. So that's why I talk about it a bit in CS1, to sort of show that sort of how we can think about arrays rather than just sort of numbers that are sort of in a column or a row, that we can think of it in more sort of a graphics type of way. And essentially this cellular automata idea is a simulation. You have cells that are on some sort of board or on the screen, and their state, their sort of representation, is determined by some specific rules. If you played the game Noida before, it does material simulations and interactions, and it's all based on cellular automata. The entire game is based on cellular automata for the most part. If you played games like, say, like Terraria or Oxygen Not Included, oftentimes their fluid or sort of gas simulation is also done using cellular automata. So these are sort of very common in things like video games where you have to simulate certain things. They're used in sort of actual science applications as well. So there's lots of cool stuff you can do with this, and it's something that I always like messing around with. The best known example is a 2D cellular automata called Conway's Game of Life that was developed in the 70s. It's a game, but not really a game that you play. You set up the initial sort of board, and then the game sort of plays itself. So there's a bunch of rules that sort of get applied to each of the cells, and then the game sort of progresses. So we are going to look at that next time and program our own version. But today is just the one-dimensional version, because it's obviously being 1D, it's going to be a little bit simpler, but it'll give you the idea of how the 2D version probably works. So cellular automata is basically just a system of cells. So that's why a grid system sort of works really well on this. So it's a system of cells with the following characteristics. They live on a grid, 1D, 2D, 3D, higher dimensions if you sort of so desire. Each cell has a state. The number of states is usually finite. So it's usually like on or off, 0 or 1, dead or alive. You might have more than 2. So in this case, they're sort of all 2 in these examples, but you could have more than 2 states. I've done sort of fluid simulations in the past that have, I think they would have like 5 states, and then even more than that, depending on sort of the situation. So that's, depends on the problem you're trying to solve. For Conway's Game of Life and for the 1D version that we're going to do today, it's going to essentially be like a 0 or 1 situation. And then each cell has a neighborhood. This is the key component of what makes a cellular automata a cellular automata. And you can define your neighborhood in many ways, and it depends on the type of simulation. But effectively, it's the region around the cell that you look at to determine the next state. So for example, if we had a 2D grid and I was looking at this cell, the neighborhood in this particular case, this drawing, would be all of these cells around me. Now this is 2D, of course, so it's going to be a little bit more complicated. There's more cells. There's 8 cells in the neighborhood, plus the center cell makes the 9. In a 1D version, it's going to be simpler. We're only going to have 3 cells that we have to look at instead of 9 cells. But that's the idea. You have a neighborhood. Now, this is defined as all of the cells that are adjacent, so the sort of direct cardinal directions and the diagonal directions. But it doesn't have to be that way. You can define it however you want to. It depends on the simulation that you're writing. All right, so I just want to give just a little bit of history of sort of where this came from. It sort of came from the 40s when sort of computers were sort of starting to get a little bit sort of more interesting. This started with Stanislaw Ulam and John von Neumann. They were interested in sort of different things, but cellular automata sort of permeated both of the stuff that they were interested in. So Ulam was interested in crystal growth, and John von Neumann was interested in self-replicating robots. And so as we sort of go along today, especially sort of this crystal growth idea, even in just a 1D cellular automata that we're going to do, you might start to see that, oh, it kind of makes sense that this could represent something like crystal growth if you sort of worked on it and figured out what the neighborhood was and what the set of rules need to be and how many states you have, that sort of thing. The most significant work was actually done by Stephen Wolfram in 2002. The work was done over the 80s. He published his sort of 1,200-page book in 2002 called The New Kind of Science, and it explored like CA in terms of like chemistry and biology and physics and stuff like that. This is the same Wolfram from Mathematica. So this is the guy, Stephen Wolfram was the guy that created Mathematica. So if you've used that software in the past, it is the same guy. All right, so let's talk about the 1D version. So the simplest CA that we can think of, the simplest sort of thing that we can have that is interesting as far as a CA goes would be on a 1D grid, 2 states, because if we only had 1 state, then that's not very interesting. So 2 states, 0 or 1 in our case. And then that makes a 3-cell neighborhood. So here's our grid. And we're going to draw something like this in JavaFX when we get to that point. And then, of course, we'll put a bunch of numbers in there. We'll put 1s and 0s. Now this right now is sort of random, but we'll get to the point where we sort of start with like a single 1 in the middle and then sort of think about how this is going to look. So this is our simplest CA. This is something that we're going to draw today in JavaFX. All right, so if I pick a cell, this would be sort of that center cell from that picture above, but we only have 1D now. So our neighborhood is only this. So we have 1 cell in the middle and 2 cells, 1 on each side, 3-cell neighborhood total. Now, when you look at this, you might go, okay, that makes sense. But what about the edge? We only have 1 cell over here now as a neighborhood. We'll have to think about that. We'll think about that when we get to thinking about the sort of rules that we come up with. So that's something to keep in mind. All right, so let's say we have that grid. The most important part here of cellular automata is time. So this state where we have a 1, 0, 1, 0, and there's some 1s and a couple zeros, this is going to change over time. That's why it's a simulation. Every single time we sort of update this generation to a new generation, and it's going to have some values in here as well, and they're going to change. And then we'll go to the next generation and they're going to change as well. And we could, in principle, you could sort of make an animation of something like this. So we're going to do something slightly different than like an animation. For Game of Life, for the 2D version, we're going to make what looks like an animation. For this version, we're going to do something slightly different, but hopefully you can get the idea. I'm going to apply some rules to each one of these cells and they're going to change. And then I'm going to do the same thing to the next generation and it will change and so on for as many generations as I want. So that's an important part of cellular automata, time, the way that you're going to change the state of the board based on your rules over time. All right, so we have a description of the neighborhood, so the 3 cells. We have a 1D grid. So we have the grid, we have the states, we have the neighborhood. So we just need to know, how does the grid change based on the neighborhood? That's the key to cellular automata. So for example, I'm going to take these 3 cells and I'm going to do some like if statements in code when we write it. And based on those 3 cells, I'm going to get a value. Now I can't just add them up because that would give me a 2 in this case, and I can only have 0 and 1s in here. So it's going to be some calculation that we do that's going to determine if I have a 1, 0, 1 as my 3 cells, then that means that this is going to be some value. Maybe it's going to be a 0, or maybe it's going to be a 1. We get to decide. So notice that that center cell is determining which cell we change in the next generation. So whatever cell we pick, we look at those 3 cells, the 2 neighbors and itself, and we change or update the same center cell in the next generation. That's how the update takes place. And in the 2D version, it's the same way. It's just 2D instead of 1D. That's the idea here for updating these. Now you might think, all right, that's cool. We can come up with some stuff. We're going to get some sort of random looking behavior. But Stephen Wolfram in the 80s, he did every possible rule for this setup for 2 states, 1D grid, 3-cell neighborhood. He looked at every possible rule that you could have. Some of them weren't very interesting, but one of the ones that we're going to pick today is actually kind of cool. All right, so let's come up with some rules. That's sort of the next piece. We have our setup. Let's do some rules. So when we blur an image in something like Photoshop, which we did our mean filter in sort of image processing stuff. It uses a cellular automata-like rule, right? We took all the values of the cells of the pixels in our image, added them up, and divided by whatever the size of our sort of neighborhood was. And then we got a value and we put it back in. That was cellular automata. Now, in that case, our pixel values were like 0 to 255. For a 1D CA, we only have a 3-cell neighborhood. We only have 2 possible values. So we can actually compute every possible configuration that those 3 cells can be in. So we have 3 cells, 2 states. How many configurations do we have? How many rules do we need? In other words, let me go back here. In other words, how many different possibilities are there of 1s and 0s in these 3 cells? Well, we have 0, 0, 0. That's a possibility. We've got 1, 0, 1. That's another possibility. We've got 1, 0, 0. We've got 0, 1, 0. So you can imagine just coming up with all the possible cases. There's only 8. It's 2 states, 3 cells. 2 to the 3rd power is 8. There's only 8 possible configurations of 1s and 0s in this. So that's what I have on the next slide. We have our 8 configurations. So when our 3 cells are 0, we need to make sure that we change the next generation to be some number. And then when we have 0, 0, 1, it's going to be something, and 0, 1, 0, 0, 1, 1. One thing you might notice here is it's just counting in binary. 0, 1, 2, 3, 4, 5, 6, 7. So if you've done any sort of binary stuff before, it's just counting up in binary. This is going to be the rule that we're going to try first. This is an interesting rule. So if you have all 0s, we go to a 0. If you have 0, 0, 1, we go to a 1. 0, 1, 0 goes to a 0, and so on. We're going to do a sort of a handwritten example. I sort of have like air quotes here, a handwritten example. But it's going to just going to be on the slides, so that you can see how this will work. And then we'll jump into programming it up. Now, I picked this rule, like I said, very specifically, because if we start with an initial state that is sort of a specific initial state, then we're going to get something really cool out of this rule. This is known in sort of Stephen Wolfram's version, this is known as Rule 90. So that's the rule that we're going to do. So if you look up like Rule 90 cellular automata, this is the rule that you're going to find. So let's do that sort of air quotes handwritten example. Here's my grid. I got 4 zeros, a 1, and then 4 zeros. So it's just a 1 here in the center. Just a 1 in the center. That's it. So let's start in the center. Code-wise, we would never start in the center. We'd start at one end and go to the other. But I mentioned that we might have to think about the edge. What are we going to do on the edge? So we'll think about that in a second. So let's start in the center. Let's pick that center cell. So we've got zeros on either side, 0, 1, 0. So for our configurations, what is that? That's 0, 1, 0. that goes to a 0. So that's what we do. We put a 0 in here. So for that center cell that we picked, we change it to a 0. Now we move over one direction, 1, 0, 0. That goes to a 1. Let's go back and look that rule up. 1, 0, 0. That changes to a 1. So we get the 0 first, then we get the 1. All zeros just goes to a 0. All zeros just goes to a 0. What about the edge? There's a few options here. It depends on what you want to do for your simulation. I'm just going to assume or sort of make the assumption that maybe if we go off the edge, then like this sort of edge neighbor value is just a 0. Or maybe what we can do actually, what we'll probably actually code up is we're only going to consider these values when we look at the sort of a center cell. That way we sort of have the edges sort of fixed or sort of static at 0. The edges, I think, will never change in the version that we code up. It'll make things a little bit easier for us, and I'll show you how we can get that sort of coded. But there's other ways to handle it as well. Things like maybe the edges remain constant. Okay, like that's what we're going to do. Maybe the edges wrap around, right? So maybe instead of just going 0, 0, I don't know what is there, the one that's over here to the right, maybe we loop all the way over to the left and we look at that one. So you could wrap around. We could come up with different neighborhoods. Maybe we have a 2-cell neighborhood that we apply to the edges. So that's the idea here. That's the idea of sort of how you deal with the edge. It's up to you, but there's a few different options for how you sort of deal with that. All right, so let's just say that we sort of keep it fixed, for instance. So if it's a 0 at the beginning, it'll be a 0 here at the end. And then we just move over and we just do the rest. 0, 0, 1. There we go. Go to 1. And then 0, 0. And then here we're just going to use the sort of fixed or maybe a 2-cell neighborhood, something to sort of keep us there. So our handwritten version of one generation looks like this. Not very exciting, but it's only one generation. It was a little bit tedious. So we're going to program it up, obviously. And I'm going to use filled squares and sort of empty squares, so black and white squares, basically. It's going to look something like this. So here's our rule 90. And I'm going to represent ones as completely black and zeros as white, and we'll have a little stroke around it as well, so that we can see where the boundaries of these squares are. So let's go code this up. This is all the slides. The next slide is just the next time that says we're going to do 2D cellular automata. So let's code this up and let's see what we get. Now I'm going to do more than just, I don't know, it was up here like 9 cells. I'm going to do more than like 9 cells, but we're going to start with the same state. We're going to start with a 1 sort of more or less in the center of our cells. So we might do like 100 cells or 200 cells. And then we're going to put a 1 in the middle or close to the middle, and then run the simulation. Well, we already know what the first iteration looks like, what the first sort of version here looks like. It's just 2 1s next to the cell that was a 1 previously, and that cell changed to a 0. Now, the other sort of result here, the other thing I want to mention that I don't have sort of in the slides, is that rather than do an animation, I'm just going to stack them up on top of each other. So we'll have our grid like this. It's going to have a whole bunch of cells. And this will be like the initial generation 0. And then I'm going to put generation 1 just right below it. So this is generation 1. And then I'm going to put generation 2 right below that, and so on. So we're actually going to have sort of what looks like a matrix. We start with, a bunch of zeros here and a 1 and zeros. And then we'd have like a 0, 0, 1, 0, 1, 0, 0, 0, and so on. It's going to look like a matrix. So that's the key to how we're going to present this, how we're going to display it on the screen. For the 2D version, it's going to look like an animation. But for this, it's just going to look like a single image. But each row represents a different generation, a generation that took its values from the previous one after applying our rules. So let's go over to Eclipse and let's get this stuff set up. So I've got a grid pane. We're going to talk about how to use that in just a moment. But first, let's make a class. What is the sort of physical object here that we're messing with? Cells. They're not very complicated either. So let's create a new class. And I'm going to call this class cell. And it doesn't need much as far as the data goes. We might want to know sort of where it is in the where the cell sort of specifically is in sort of row and column way, but maybe we'll add that if we think we need it. The main thing it needs to know is the state. This is an int state, and I'm just going to sort of initially give it a value of 0, or maybe put it in the constructor. This is going to be state equals 0. That's really all it needs to know, sort of math-wise. It just needs to know what is its state, and we're going to start it at 0. And it needs to be able to have like a setter and a getter. So public int get state, and we'll return state, and a public void set state, because we'll probably want to change the state at some point as we go through. We'll at least want to change the state of a cell, for example. So we say this dot state equals state. Now, in order to use JavaFX with this, we're going to need some graphics. So as we've sort of been working with some of these graphics things, let's do, you sort of know where this is probably headed. We're going to create a private rectangle that I'm just going to call R. And that needs to be imported from JavaFX. And then in here, I'm going to say R equals new rectangle. And I'm actually just going to put its position as 0, 0. And let's make the size, I'm trying to think of how big I want the window to be. Let's just hard code it right now to be 10. Actually, let's use 5. So we're just going to create a rectangle, and it's going to be at position 0, 0, and it's going to be 5 by 5 pixels. Sounds reasonable enough. Let's give it a color to start with. Our state starts at 0, so I'm going to say r.set fill. This is going to be color.white. And let's give it a stroke as well. So let's say r.set stroke. So this is going to be, a stroke color. Let's make the stroke black, so we get like a black line around the rectangle. Some of the other properties we might want to set here, there is a set stroke width. Probably want to make that just a value of 1, so that it's a very thin stroke. We have just 1 pixel. We don't need it to be any larger than that. And then we probably want a way to get our graphic. So I'm going to say public rectangle get graphic. And we're going to return R. So that's the idea here. Similar to all the stuff we've done before with our snake game and with the other graphic stuff we've done. We got a state and we have a rectangle. Now with the set state, this is an interesting one. We sort of default to this being a white fill and a black stroke. But if the state equals 1, then we need to set the fill to be black. So whenever we set the state of the cell, if the state's 1, it's black. Now, we don't flip these around. It's not like we're going to be changing the state more than once, and you'll see why once we get to the code. But in principle, you probably want to put something in here like an else, and then use the white here for that. We should probably do this, but we're not going to actually be calling this more than once. But this is sort of the general idea here. All right, so when we set the state, we set the color appropriately. We start with white with a black stroke and a very thin line for that for the outline for the stroke color or for the stroke width, and then we've got sort of a small 5 by 5 rectangle. So let's create a whole bunch of these. let's create an array of cells, and then we'll draw them out onto the screen. Before we do any stuff with rules or any of that, or any of the calculations we're going to do, let's just draw a grid on the screen, because ultimately that's something that we're going to have to do. So I've got this grid pane. Let's create a matrix of cells. So I'm going to create a cell 2D array that I'm going to call, let's call this my my board. This is going to be a new cell. We don't necessarily want this. We want a new, we want a new cell array like this. Let's make, we're going to need to put numbers in here, but I want to create a couple of extra variables for us. Let's do rows, and let's just do a 10 by 10 for the moment. The rows and columns here. So we're going to have rows and columns. Now I need to loop through this board that I've created, because it's created an array of cells, but it hasn't actually created any of these cells yet. So I need to loop through we'll do rows first. So think of this as sort of the setup of our cell array. Setup of cell array. And we'll do a J. So we are going to have sort of multiple loops that sort of look like this to get everything set up properly. So that's less than columns, J++. And now each cell, so I'm going to say board, and we're going to use row and column. So that particular cell in the board, that will be a new cell. That is, in this case, it's creating, so let's see, create each cell object in the array. So at the beginning, just by doing this line, it doesn't create any of the cells. We never call new cell. We never call the constructor. So I have to go through each individual element of my array, my 2D array, and create a new cell in there. That gives me a whole array of cells that are state 0. They have a rectangle associated with them with a white fill, a black stroke, and a very thin stroke width around the edge of the rectangle. So that's what that piece does. Now, how do we add these to our grid pane? The nice thing about that is it's super, super easy. I could do it in this same loop, and I'm actually going to do it in the same loop. We could write a separate loop to do it, but doing it in the same loop here is fine. I'm going to say p.add. And what's the child? It's the board, ij. What's the column? That is j. What's the row? That is I. Oh, sorry, this should be board ij.get graphic, because this is a cell. We're getting the graphic, and we're adding it to the j column and the I row in our grid pane. There it is. It's a tiny little grid, but there's a very good reason for that. And actually, maybe we'll make these a little bit larger. Actually, maybe rather than 5, let's do like 8 or something. Make them just a little bit bigger, because I know it can be a little bit tough to see that potentially on my screen, depending on the resolution and whatnot that you're watching it in. So let's make these a little bit bigger here. So we have a little bit bigger squares. And of course, it doesn't fill up my whole window because I'm only doing 10 by 10. But our idea here is to do something like, say, like 100 by like 200, something like this. Actually, for rows, let's do 200 rows and 100 columns. I'll flip that around. So I'm going to do something like this, so that we get a very large grid. There you go, something like this, maybe. I don't know how many more rows we got left down here. Yeah, I'll probably reduce the number on there, but that's the idea. We want a very large grid for the calculation that we're going to do. And remember, based on the slides, each row is one generation. So this will be the 0th generation. The one here will be, the next one will be the 1st generation, 2nd generation, and so on after we start applying our rules. So I'm going to use let's actually get the grid set up to be the size we want. So let's say for rows, let's just do 100 rows. So this should make sort of a square looking grid here. So yeah, something like that. I think that's probably fine. Let's set this up to be 100 and yeah, actually let's do like 90 columns. Maybe like 91 columns or something. Something that's sort of odd, but is sort of large enough. I don't know, maybe like 101 columns or something. Ultimately, it doesn't really matter, but we would do something like this. Now I'm going to take the center cell, in the very first row and set that to be 1. So it'll be somewhere over here. We'll have a black cell. That'll be the equivalent to what we were doing on the slides. So let's do that. Let's set the center cell in row 0, which is the initial gen 0 to 1. So I'm going to take board. I is the rows. So we're going to take row 0. And we're going to take the j being columns divided by 2, doing an integer division. And I'm going to say dot set state 1. And there's our black cell. So that's the start. So this right here is all the setup. It's all the setup we need to do. All the other generations are going to fill up based on our rules, but we have to set the initial one. All right, so now we apply rules to each generation. All right, so let's go back and look at the slides real quick. So these are our rules. If we scroll up, you can probably scroll up over here and see sort of the various sort of numbers here like this. We're going to have to look at the previous cell, the previous row, and the cell to the left of us and the cell to the right of us. That's how we're going to determine this. So let's do, and I'm just going to use a big sort of if block when I do this. So hopefully it sort of makes sense. But let's start with our loops. So I'm going to do int I equals 1. See why in just a second. I less than rows, I plus plus. This is our rows equals generations. So I don't need to do row 0 because row 0's already been set. I need to start with row 1. That's generation 1. So that's where we're going to start. And we're going to loop through. I'm going to change this here in just a second, and I'm going to explain why. But we're going to loop through the columns. That's the values in the particular row. So this is each grid space in the ith generation. Now I'm going to start at 1 and go to less than columns minus 1. So what does that mean in this case? It means that I am not going to consider the edge cells, so all the sort of edge cells here. I'm not going to consider these, the very edge cells, to be a center cell. The only cell I'm going to look at, the last cell I'm going to look at on the right is the cell next to the edge cell, and the only one here is the second cell, the second column. That way I never have to worry about going off the edge if I try to look to the left or to the right. So hopefully that makes sense, and that's just done very simply by ensuring that my J index starts at 1, so I can look to the left and find 0, and goes to less than columns minus 1, which means I can look to the right and find the last cell. All right, so that's our loop. Now we need to apply the rules. So the cell that we're working with, the cell that we're updating, is going to be the IJ cell. The cells that we look at to determine the rule So let's create an int. I'm gonna make this a little bit more explicit than what I sort of had already prepared. We're gonna see the previous gen. So the previous generation is what? I minus 1. That's the previous generation. That's the one that we're going to be looking at to determine what the rules are. We're also going to need a left, center, and right. So that's my neighborhood, right? Well, the center cell is easy. That's just board I, J, because that's the cell that I'm looking at. The left cell, actually, this should be, sorry, this shouldn't be I here. This should be the previous gen, cell J, because I want to look at the generation before where I am and the J cell. To the left, this would be board, the previous generation. That's what I'm looking at. And I need J, but now we're going to do minus 1. That's the cell to the left in the previous generation. And then we have this right equals the board, the previous gen, and this would be J plus 1. Yeah, and this needs to be get state. To actually get the value. All right, let's go over here. So the idea here is this, right? I'm looking at this. This would be I equals 0. So this one here would be I equals 1. So I'm going to use, and this, let's say this is J equals 0, 1, 2, 3, 4. This is J equals 4. So I'm going to look at I equals 0, J equals 4 for this one. I'm going to look at 0, 5 for this one, and 0, 3 for this one to get all 3 of those states. And I'm always looking to the previous generation, not to 0. I don't want to look to 0 every time. I just want to look to whatever generation I am on minus 1. That's why I'm looking up here. The next generation down here would be looking up to these guys up here. That's the idea. That's what I'm doing with the code that I just wrote, so that it's just the previous generation is I minus 1, and then we have the left, the center, and the right based on the previous generation and a different J for each one. And of course, get state, because the board at this location is a state or is a cell, and so then we need to get the state. Once I have those states, then it's just a matter of applying the rule. So I'm going to create an int called new state, and I'm just going to set it to 0 here to start with. And then we're going to have our rules. So we're going to do something like if left equals 1 and center equals 1 and right equals 1. What is that? Well, we can go look at our rules here. If we have 1, 1, 1, our new state is 0. So I'll say new state equals 0. Technically, I didn't have to do it because I already set the new state up here, but I want to be very explicit as to what this is. And then we'll do an else if. And we'll keep going with this. We'll say left if left equals, let's do 1 and center equals 1 and right equals 0, then this one happens to be new state equals 1. And we're just going to keep doing this for all 8. So there's our versions. Yes, this is something where you're copying and pasting, and this is not the ideal way to do it. The better way to do this would be to have a lookup table and do it that way, but I want to be very explicit about what this looks like. So I'm going to fill in the ifs here, and you can sort of pause this or take a look. But basically, I'm just counting in binary. I'm going to do it from, I guess, the bottom up here. So the next one here would be 0, 0. And then we'll have 0, 1, 1, and then 0, and yeah, it should work there. And then we'll have 0, 1, and then all 0. So it should be sort of binary, sort of going up. So we've got 0, 1, 2, 3, 4, 5, 6, 7. Yeah, so that should work. So this is going to be 0, 1, 0, 1, 1, 0, 1, 0. So that's what the rules look like. We can actually go in and actually change this. We can change what one of the rules does, what one of the states is, and we can see how that changes our stuff. So now we have the new state. So let's go and make sure that the board, so let's see where we're at here. So I'm going to say, finally, I'm going to say change the cell to the correct state. So I'm going to say board ij. Now I do use I because that's the current generation that we're on. Dot set state, new state. And that's it. That should give us exactly what we want. So let me just do a quick recap. I created a 2D array of cells. This is empty right now. This is sort of null for every single case. So I had to go through, make a loop, create a new cell for each one, and add it to my grid pane at position column J, row I, and I used the get graphic. So similar to the get children stuff that we've done in the past for our panes. Then I took the board position at row 0, which is the generation, and the middle of the columns, and I set the state to 1 to give us a black square in the middle. Then I loop through all the remaining generations, so all the remaining rows, skipping 0, starting at 1. And I loop through all of the columns, except for the first column and the last column. I just keep those as being a state of 0. And I say, all right, the previous generation is I minus 1, so that would be 0 for the first time through. We have the left, the center, and the right. We get the state for each one of those. And then we use those to compute what our new state is going to be. Once we get the new state, then we set the board at ij to that new state. So let's see what we get here. Hopefully this is going to look all right. There we go. This is a fractal. This is why Rule 90 is actually really cool. Let me do more columns. Let's do like 201 columns here, so I can see it a little bit wider. So this is a fractal. And you can see if we sort of look closely up here at the top, there's our center, and then there's the one that looks like we started a triangle. Sort of have a 0 in the center now, and then 2 off to the side. If we look back at the slides, that's exactly what we came up with here. So if we kept going by hand, we would end up with this triangle. This is what's known as Sierpinski's triangle. Some of you may have seen this before, sort of elsewhere in other contexts, but this is a way to create a fractal just using 1D cellular automata with a simple rule and a very simple amount of code to write. We can generate a fractal, probably even simpler than our Mandelbrot set. And if you keep going with this, you can make this as big as you want. It's going to keep making this sort of Sierpinski's triangle stuff. So that's a cellular automata, a 1D. Each generation is stacked up on the sort of stacked sort of below the previous generation. That's the way we did it here. So if some of the code here was confusing, that's definitely all right. But make sure you can go through and understand how it works, because this sort of 2D array stuff and this sort of, okay, I'm making like a matrix of cells and things, that stuff does not go away. You will be seeing more of that sort of stuff again. And for our 2D cellular automata, that's the whole point, is to have a 2D grid. So this is sort of time. You should think of time in cellular automata is going down. Let's change one of the rules. I don't know. I don't sort of know off the top of my head what all the rules are. Most of them are not very interesting. Let's just change one here. Let's just change this one here. That if we have a 1, 0, 1, let's say that turns into a 1 instead of a 0 now. This is probably not going to look very good, but we'll see. There you go. We still get a triangle, but now it's certainly not a fractal, certainly not Sierpinski's triangle. But it just sort of fills in sort of every single other one. And then maybe let's change another one over here to, so I've turned that one back. Let's change this one over here. It's just a different rule. There's 255 of these rules. So it's just a different version of it, and it gives you something different. So there's some really cool stuff that you can do with these. There's some cool other sort of fractal looking things as well, depending on the rule that you use. So you can certainly look up the different rules or look up the interesting rules. But this idea is the cellular automata idea, where you have some sort of grid, typically some sort of board, and you're just looking at your neighborhood. And from that neighborhood, you're determining what the new state should be. That's it. That is cellular automata in a nutshell. There's lots of other cool stuff that we can do with it. I'll show you some other stuff next time. To the game of life is the obvious one. We're going to actually code that, but I have other ones as well. I'll see if I can pull out a video of one that I created a while back. It's a fluid sim, and it's literally just a cellular automata. There's just, instead of there being just 2 states per cell, it's literally a square cellular automata, so just a grid like we have here. But I think there's 5 possible states. So it's simple. There are the rules, are a little bit more complicated since you have 5 possible states, but it's simple in that it's still just cellular automata, but you still get these cool wave-like patterns when you start running the simulation. So there's some cool stuff with that. So that's all I had for you guys today. Hopefully that was somewhat interesting. We'll do the 2D one next time. A little bit more complicated code, but ends up with a much cooler result, even though we ended up with a fractal here. So until then, I'll see you guys next time.